Today I want to start off a little bit differently. I want to talk about Russian nesting dolls. Okay, so you might have heard of these things. Like Matryoshka dolls is another term that you'll hear for them. And if you've ever seen these, maybe in somebody's house, they're typically ceramic. They're made out of, or maybe porcelain or something like that. And each doll fits neatly inside a stack. So this doll would fit into that doll, which would fit into that doll, which would fit into that doll, which would fit into that doll. So at the end of the day, you have one doll that contains all these underneath. So one doll, when it's in one doll mode, it's this very solid mass. It has the volume is almost identical to if it were just filled with cement or something like that, or pure ceramic. Versus, when you separate each individual one, each of these is hollow inside. So what's neat about this is that the mathematical analog to what we're going to talk about today is very much related to the idea of these nesting dolls. So we've discussed this idea of a disk and washer method. We've talked about the idea of taking a function and kind of revolving it, doing kind of that pottery throw to get a solid mass. And we did that before by stacking these disks. So we took the area of disks and we would stack them together. And then if we did it with, decreasingly thin strips, that would smooth out and get you a smooth surface, right? So we're going to do the same idea here, but instead of using solid disks, what we're going to use is hollow. Think of them as Matryoshka dolls, but they're really defined based upon cylinders. So we did cylinders before because we did the disc, the solid volume of a cylinder. But instead what we're going to do is focus on the surface area of a cylinder. Now if you go all the way back to your study of elementary geometry, maybe even to sort of like middle school geometry, you might have discussed this idea of a surface area of a cylinder. And that is the circumference of a circle, not the area, but the circumference of a circle multiplied by the height of the cylinder, right? So it's this idea if you unrolled the cylinder all the way through to make a flat rectangle, this is the area that flat rectangle would have. So if I take a rectangle and I wrap it, what I do is I can take the height, and then I need to convert the base into something like this. But and that would give me a cylinder with those dimensions of the radius and the height. Anyway, but we're going to use that idea. So what we're going to do here is we're going to look at a function. We're going to say, okay, I've got a function, this blue line here, function f of x. Now in the washer method, or the disk method, we would rotate that around the x-axis because it's defined in terms of x. And if it was defined in terms of y, and sometimes we had to determine a function that was defined in terms of y, we could rotate it about the y-axis. But with the shell method, what we're going to do is we're going to do the opposite. We're going to say, okay, at this particular height, I can find a radius that I come away from the y-axis. I can find a height, and I can define a cylinder there. And then what I can do is I can go a little bit more out. I can define a cylinder there, and a cylinder, and a cylinder, and a cylinder, and a cylinder. And what I'm doing is I'm summing up these shells. So I'm stacking them inside of each other, much like the nesting dolls, just like the Matryoshkas. I'm saying I've got a cylinder, and then I wrap another cylinder, and then I wrap another cylinder, and wrap it. And by wrapping those cylinders around, and unlike the Matryoshka dolls, each of these fit neatly in. On these, what you're going to find is the wrapping cylinder out here is not going to completely consume the cylinder above it, but it's going to wrap around it. So each cylinder is going to wrap around as you go outward. So what can we do? Well, we can take this idea of saying, okay, well, I know that the surface area of each individual cylinder is 2 pi RH. Okay, simple enough. So if I know that 2 pi RH is that, how do I relate that to my mathematical construct here? Well, the radius of that cylinder is just my x value that I'm currently at, and the height is the function value. So I say, okay, well, that's 2 pi, that's my radius, that's my height, so 2 pi RH, and then I go from A to B. I sum from A to B. So I define this function 2 pi x times the function dx. And I can generate, and of course that integral is going to be different depending on the actual function you're integrating. What this does is this gives us a couple of things. There are a couple of really neat things that this gives us. The first one is that this allows for perpendicular revolution. What do I mean by that? Well, in the washer method or the disk method, if we had to say we had a function defined f of x and we wanted to revolve it around the y-axis, you remember that we had to rewrite that function in terms of y. You know, we had to say, okay, well, that's f of x here is actually y there, and then that revolves. Now, you had further problems if this wasn't an invertible function, and I don't believe that we discussed anything like that where we had non-invertible functions. Think like a sine wave or something like that. And if you had non-invertible functions, you would have actually had to define multiple functions of y based upon like segmented domains. It would have been pretty nasty, so I wouldn't recommend that. What the shell method allows us to do is completely get rid of any of that. It says, look, if I've got a function defined in terms of x, but I want to revolve it around the y-axis, I just use this thing. And similarly, if it's defined in terms of y and you want to revolve around the x-axis, you can do this. That's the whole, one of the biggest benefits there. The second benefit is that it gives you another tool in your kit. So what you're going to find in a lot of cases is that it's really important to be well versed in many techniques, because you're going to find some functions where if you try to do it with the washer method, it's actually easier, but you have to find that inverse function. But finding that inverse function and then integrating the square of it is actually easier than trying to set up some sort of x times that. And sometimes it's almost impossible to do it this way. You have to do it the other way. But having multiple methods in your kit allows you to choose strategically, maybe is the right word, but smartly, so that you can end up with a result that's much simpler, right? The more tools you know, the less you have to do it the hard way. So we're going to do some examples with the shell method, and hopefully this will get you comfortable with this, because this is going to set up an additional concept that we're going to study in the future.